Hello everybody. So today we will be discussing about differential equations, but boundary value problems. How is it different from what we did in the last class? So what we did during Runge-Kutta or Euler was we had first order and then we learnt about second order differential equations, where we gave the two initial conditions, the value of say x at time t equal to 0 and dx dt or velocity at time t equal to 0, and then what we did is basically calculate the values of x at subsequent times. So, at time t equal to 0, time t equal to 0 plus h, time t equal to 0 plus 2 h, and so on. So, we basically had the value of the position say and the velocity, or just let us talk about dx dt or the first derivative of the function at different instances in time, right. And we basically integrated the equations from time t equal to 0 to time t equal to whatever we want, and we also looked at many coupled differential equations. Basically various particles were moving with each other, with respect to each other, and the forces depended on the separation between the two neighboring particles in the y direction. However, the problems we are going to discuss today are different. We are not going to tell or give the initial conditions at time t equal to 0, where but we are going to give the boundary conditions, which means at one end of the interval and the other end of the interval. So, let us be more specific. Let us suppose that we have a differential equation d2y dx2 minus 5 dy dx plus 10 y of x equal to 10x, right. And we have to solve this differential equation. This equation can also be written as y double dash x, where the double dash basically stands for d2y dx2 and y dash stands for dy dx, and so on and so forth. And the boundary conditions are y at x equal to 0. So, y at x equal to 0 equal to 0 and y at x equal to 1 equal to 100, which can also be written as y 1 equal to 100, right. So, here you have two conditions, but now they are given at the two ends of the interval, and you have to find the value by solving this differential equation. You have to find y as a function of x for the intermediate points, right. So, this is a simple toy problem, but the way we are going to solve it is the so called finite difference method. And the finite difference method, the things that we learn are particularly useful to solve partial differential equations, which will be the topic of the next class. So, but first let us figure out how we do finite difference methods and solve this particular differential equation for these boundary conditions, right. And we have to solve this get the solution from x equal to 0 to x equal to 1. So, just to look at it graphically, so you have to solve y as a function of x by solving this differential equation. You know the boundary conditions, that is at x equal to 0, you know that the value of y is 0. You know that at x equal to 1, right, the value of y is 100. So, this point and this point, you know the value of y, and by solving this differential equation you have to essentially figure out what is the value of y at the intermediate points. Now, I would request you to remember when you learnt about differentiation and integration in class 12, and what you learnt in class 11 or 12 was, suppose you had a curve like this, right. Then at each point what you could do is basically calculate when you change x in this direction, suppose how much would be the change in y, and then you would say okay, dy by dx, the change in y with respect to x, and that you would calculate as dy dx, and then you will take dx the limit tends to 0. right. And similarly, at each point in space, you could also calculate the second derivative d2y dx2 by taking the suitable derivative of dy dx. Here you have the opposite problem, where you have expression, you have d2y dx2 dy dx at different points in space, and you have to solve the differential equation to get y as a function of x. What we are going to use is basically write these double derivatives and single derivatives as difference equations, right. So, here you are saying that okay, you are basically writing the difference in a neighboring value of y. So, when you are calculating the y at a particular point, say I here at this point at a particular value of x. So, you are trying to calculate the derivative, you are writing the expression for dy dx by discretizing space and saying okay, then that I shall write down the derivative as the value of y at a neighboring point, say I plus 1, and at another neighboring point the change in the value of y by the interval 2h, which would be equivalent to dx 2 dx, right. And similarly, you have this expression for the double derivative, and these can all be derived using Taylor expansions. I am not going to go into that. I am rather saying that if you accept these and you can derive those, how to basically solve the differential equation in a hands on manner. So, that is what my focus is, and to dock in detail, and we have to find the value of y as a function of x over this interval, right, from x equal to 0 equal to x equal to 1, and we to solve it on the computer, we can't work with dx or the interval going to 0, where we need a finite value of the interval, say h. So, dx tends to 0, but h always has a finite value. What we do is discretize the space. So, suppose this is x equal to 0, right, this point, and this is x equal to 1, and we divide this entire range between x equal to 0 and x equal to 1 into discrete points. So, suppose this is x equal to 0 and this is the value of x at a distance h from this point, and so each of these intervals are called h. So, h can be suppose 0.05 as an example. So, then so at this point x would be 0, at this point x would be 0.05, at this point it would be x equal to 0.1, and so on so forth. Now, we can call each of these points at which we are defining these values of x to be I. So, this is I equal to 1, this is I equal to 2, I equal to 3, I equal to 4, and so on so forth, and it goes up till I equal to p, right. So, what is the value of p? Well, p would be xf, the final value, in our case it is 1, minus xi, the initial value, in this case xi equal to 0, divided by the interval. So, it depends upon how finely you divide this entire range from x equal to 0 to x equal to 1, into how finely you want to divide it. You can choose h equal to 0.05. In that case, you shall divide this entire interval into 20 points. So, p equal to xf minus xi, the xf for final, I for initial, by h being 0.05, and then you will get p equal to 20, and you can take the integer and then you get the number of points. But if you take suppose h equal to bigger 0.1, right, then you will have 10 points between xi equal to 0 and xf equal to 1. I will run from 1 to 10, right. Now, at each of these points, so you have discretized space along the x direction. Now, you have to find the value of y at each of these points. If you like, you can say we have to find the value of y for I equal to 1, what is the value of y at I equal to 2, and so on so forth. And at each I point I, you have a certain different value of x if h equal to 0.05, then x 1 will be 0, x 2 will be 0.05, x 3 will be essentially 0.01. So, you have to calculate at each of these I points the value of y and basically plot y as a function of x, which is your solution, right. Now, in the differential equation where you have double derivative and a single derivative, you can write down y dash, the single derivative, as y equal to I plus 1 if I is any particular point, then the value of y. So, if this is suppose I here, then what is the value of y at I plus 1? What is the value of y at I minus 1? And of course, you do not know that is what you are after have to find out, right. But if you knew its neighboring values, then you could find out or write down an expression for y dash, the single derivative. And similarly, y double dash, the double derivative, can be written down as this. So, y at I plus 1 minus 2 y I and y at I minus 1, right. So, you have basically discrete expressions for the derivatives at this, using the values of y at discrete points in space. That is why you called it difference equation and not differential equation, because now you are writing it in discrete values of y and at discrete points in space, not continuously. You have discretized this space into certain points. Now, if you have these expressions for y dash and y double dash, right, then what you can do is substitute these expressions, these difference equation expressions in your original differential equation. So, basically here instead of y dash, I have written the expression for the difference equation y I plus 1 minus 2 y I y I minus 1, where I runs from I say 1 to 20. If h equal to 0.05, it could run from I could run from 1 to 100 if h was 0.01, right, so on so forth. And here I have written the expression for y dash, right, and this is plus 10 y. So, basically at each point you can write down y I, and you have to solve for y I, of course, into 10 x I, whatever the value of x is at each point at for I equal to 1 to y equal to p, right. So, what you have done consequently is basically converted this differential equation into an algebraic equation. So, if you multiply h square over this entire equation, what you get is y I plus 1 minus 2 y I minus 1 into 5 by 2 into h, because there is a denominator, there is h, and you are multiplying by h square, right. Similarly, you will get a expression of h square here and 10 x I h square, right, because you are multiplying the entire equation by h square. And now you can rearrange the terms and you can write y I as 1 minus 2 minus 10 h square plus 1 minus 5 h by 2 y I plus 1 plus 1 plus 5 h by 2, h is this distance between grid point dx if you like, to y I minus 1 minus 10 h square x I. What is the message? If somehow you knew the value of y I plus 1 and I minus 1. So, if you somehow knew it, or even if you guessed it, Okay, suppose you try out with a trial solution, you do not know what the solution of the differential equation is, but you could have a trial solution. Especially since you have an idea of the limits, you know that at x equal to 0, y equal to 0, and at x equal to 1, y equal to 100. So, let us suppose the solution will be something close to a straight line, it is a trial solution, and then you say that okay, let me see whether can I solve iteratively, can I move closer to the actual solution iteratively in by some method, and finally arrive at the correct solution of the differential equation. So, that is the aim, and with that aim, with suppose a trial solution, you knew the value of y I plus 1 and y I minus 1, right. Then you could calculate an improved value, improved or more accurate value of y I by solving this so called difference equation, right. So, that is what our aim is. So, basically what we are trying, that at different points, grid points along the entire range, you have x at different points 0.05, 0.1, 0.02. At each point you have a guess for the value of y I and y I minus 1 and y I plus 1 over the entire range. You have a initial guess solution, right, and using that guess solution you basically calculate improved value of y I over the entire range. Okay. So, you have a guess, you get an improved calculation of y I over the entire range, and you keep on doing it iteratively, right. So, basically if so there would be, if the NOP, number of points p in the integer value of his NOP, if there were NOP grid points, you can in your old or initial guess of the value of y at each of these grid points, you could store in an array called old y, right. You just suppose it stores the initial value of y for all values of I, that is at each value of x I, right, and using this formula here, this formula, right, you can basically at each point, at each grid point, calculate a better and improved value of y 2 and then y 3, sorry, and y 4 and y NOP minus 1, right. And then what you do is basically store these improved values of y 2, y 3, y 4, so on so forth into old y. You save them and use that to have better estimates of y 2, y 3, y 4, y 5 over the entire range. You keep on doing this iteratively and your solution will relax or converge towards the correct solution. Now, for that what you need is that you need a reasonable guess of or initial guess of the solution. If the solution is very far away, the initial guess is very far away, then this, by doing this process iteratively, you are not going to converge to the actual solution, right. So, you need some estimate, using some analytical methods that okay, this should be the solution. Yes, I cannot solve it exactly, but this could be the nature of the solution. You can have a guess from the boundary conditions as well, and then basically the system, if you have a reasonable guess not too far away, then basically you will iteratively move, converge or relax to the accurate and correct solution. Note, when I said that you can update the values of y for each of the grid points, I started from y equal to 2 and stopped at y equal to NOP minus 1. right. NOP is basically the number of points which I refer to as NOP. You can also say P basically. If you take the integer of P, you get NOP. So, those two, the boundary points I did not update because the boundary points are fixed, they do not change, right. When I do the iterations, the boundary points, the solution at the boundary points are given and they do not change. So, you do not update that, but any point between the range, between the boundary is iteratively corrected for, and you slowly relax to the correct solution. So, that is basically what the plan is. That is how you solve a differential equation where the boundary conditions are given. So, you use the boundary conditions, write down d2y dx2, d3y dx2. If you had higher order terms, there are formulas given in books, you can look up the derivation. Basically Taylor series expansion, and if you have the expressions given, then you substitute them into the differential equation, convert it into an algebraic equation as we did here, right. Then write y I in terms of the values of y of its neighbors, and then you solve it. You have an initial guess where you have y I defined at each of these grid points, and then iteratively you say that okay, if this condition is to be satisfied, the value the improved value of y I should be such and such as per this equation. I mean, if you have a different differential equation, of course, this expression will be different, right. This is derived from this differential rather difference equation, right, and then you solve it for each value of y and use this to get improved estimates of y I and so on so forth. So, basically what I have written here in this slide is what I already said, that every time you calculate the improved values of y using the old values of y, and then you save the values of y into y old for all I, and then again calculate the new y. So, how should the code look like? How should the code look like? It should be basically do. So, there should be a do loop, but look, this is an open ended do loop because you do not know how many times you have to iterate to reach the improved and the so called correct value, right. You will not ever reach the exact value, you will never reach that, because after all you are discretizing space, there will be some rounding off errors, but you can reach reasonably close to the actual solution of the differential equation. But in how many iterations, that is unknown. So, here what I have given is an open ended do loop. So, do and do here, right, and say okay, before that you have some guess for each value of y I, the value of y at each of the grid points, and suppose y old stores that. The basically y old is an array and it is of length p, of course. So, I have first saved the value of y old for the purpose of the do loop, right. So, suppose you stored the value of y I need, the initial values in this array y, right. I had made a mistake, so I added this statement, and basically y old you. So, the value of y is stored in y old first, and then you update the value of y here, right. So, it is this same formula, do I equal to 1 to number of points, rather it should be 2 to number of point minus 1, right, because you do not have to basically update the boundary points, the end points, and for all I in this range, basically you update the value of y using the same formula that I wrote, where for d1, so d1 is nothing but this quantity, the same as this quantity. You do not need to calculate this quantity every time, hence you can calculate d1, some dummy variable right at the beginning of the code, so that you save basically computational resources. So, d1 into y old, the older value whatever was saved, I plus 1, then d2 is nothing but 1 plus 5 h by 2, the same as expression here. H of course is the difference between grid points dx. So, d2 into y old, the older value of y at I minus 1 minus d3 being this into xi, right. So, at the end of this do loop, you have a new value of y stored, that you store in y old again, and repeat this, and you keep on doing this iteratively. And this, so with every iteration you will have improved values of yi, which means that suppose that if your guess for the initial condition was the straight line joining x equal to 0, y equal to 0 at x equal to 0 and y equal to 100 at x equal to 1, suppose your initial guess was the straight line, with each iteration you will have this line as an improvement, and then this line, and so on so forth, and then finally your final solution would be this, right. That so this blue line where you have the value of y at each of these discrete points. The question is when. So, how many times will you iterate? When will you go out of the loop? Here you see, as I told before, that I have not given any particular number of iterations, because number of iterations, number of times you have to iterate is typically unknown. So, to get out of this loop, when you have the final solution, you shall need a condition of how to exit this loop, right. And suppose you define a variable called cond for condition, and cond equal to 1, suppose you set it equal to 1 when a certain criteria or condition is satisfied, and depending upon the value of y, and if cond equal to 1, then you say okay, exit this loop, and that is your final converged value of your yi. Okay. So, let us suppose your condition. So, the condition when cond will become equal to 1, when you will exit the loop, you can set that to if yi, that is the new values, the updated values of yi in this particular iteration minus y old, the previous value of y, if this difference is less than some limit, say 10 to the power minus 3 for all the values of I, then you set cond equal to 1, and then if cond equal to 1, then exit. But you have to check that for each value of I, for each of these grid points, the grid points between the boundaries, that this, the difference between the older yi and the newer yi is less than a certain limit. So, how do you implement it? Now, suppose you, so basically it is here that this code will go in, here you are constantly updating, but after every update you check whether the condition for convergence to the final value has been reached or not, and if the condition for convergence has been reached, you exit. So, basically here you are checking whether you have reached convergence or not. So, at this part what you do is the check, and how do you check? You say okay, do I equal to, again this should be 2 to NOP minus 1 between the boundary points. If yi minus y old, the older value is greater than, if this condition is not satisfied, if it is greater than your limit, right, 10 to the power minus 3, then you say cond equal to 0, and if cond becomes 0, then you do not exit the loop. So, you have set cond equal to 1, the condition equal to 1 before the loop. In the loop, if any of these points for any I, if cond, if the condition is not satisfied, you change the value of cond to 0 and it remains there, right. There is no condition which is given that it will become again equal to 1 between this loop, right. And if cond equal to 1, then exist, then exit, but if cond becomes 0, if any of this condition for any I is satisfied, then you do not exit it. What do? You go back here, you set y old equal to y, update yi, again check if any for any I, if the difference between the new value and the older value is less than the criteria that you have set, the convergence limit that you have set, and you keep on doing it.